You can spend hundreds of hours labbing network scenarios and memorize every command, but still bomb the interview. Knowing how a network operates is a separate skill from being able to articulate it while 3 senior engineers watch you from across the table. Hiring managers often use the Cisco ASA as a litmus test for security logic. Because its architecture mirrors the core principles of most modern stateful firewalls, it provides a baseline for evaluating how a candidate thinks about traffic flow. But candidates fall into a predictable trap. They get nervous and start rambling. They list every configuration detail they can remember, delivering unstructured answers that practically invite the interviewer to ask dangerous, highly specific follow-up questions. Beating the interview process means proving you won't be a liability. They aren't looking for a human encyclopedia. They are looking for someone who can communicate technical concepts with structured, actionable competence. The DEU framework turns rambling into precise answers. First, definition, establishing a factual boundary. Second, example, describing a concrete application to prove you understand its behavior. Third, use case, connecting that example to the business value it provides. This structure forces you to stop before you over-explain. It signals to an interviewer that you can prioritize the most relevant information, a trait they look for when hiring senior-level engineers. Let's apply this framework directly to one of the most common ASA interview topics, interface architecture and numeric trust levels. We start with the inside interface, the trusted internal LAN, assigned security level 100. On the opposite end, the outside interface is the untrusted public internet connection, receiving level 0. In the middle sits the DMZ, a semi-trusted zone for public servers, given level 50. These numeric values control default traffic flows. The ASA automatically allows traffic to pass from higher trust levels to lower ones without additional rules, but this creates an operational trade-off. If you want someone on the internet at level 0 to access a web server in your level 50 DMZ, you have to explicitly write configurations to permit that untrusted inbound traffic. The use case for this architecture is straightforward. Placing public servers in a dedicated DMZ ensures that if one is compromised, the intruder still has no direct path to the trusted internal LAN. That explicitly permitted traffic is controlled by access control lists, or ACLs. They act as the strict gatekeepers that either permit or deny packets from crossing between interfaces. This diagram illustrates how the firewall processes ACLs. It reads rules strictly from top to bottom. The first matching rule is applied, and the firewall stops reading. At the very bottom of every list is a hidden default rule called the implicit deny. Because of this implicit deny, any traffic that fails to match a specific allow rule higher up in the list is automatically dropped by the firewall. This demands exact precision. If you accidentally place a broad deny rule at the top of your list, it will instantly block legitimate traffic, regardless of any permit rules written underneath it. When you explain ACLs in an interview, the use case is clear. They are the primary mechanism for ensuring that unauthorized traffic is filtered out and never traverses the firewall. Once traffic is allowed through, it usually needs to be routed to the internet. This brings up Network Address Translation, or NAT, which translates private internal IP addresses into public internet IP addresses. This split screen compares translation types. On the left, PAT maps many internal users to one public IP using distinct port numbers, providing efficient internet access. On the right, static NAT is a strict one-to-one mapping, linking a single private IP to a fixed public IP. Here is the architectural trade-off. PAT works for general browsing, but it fails if external users need to consistently find a specific server. Hosting internet-facing infrastructure strictly requires the fixed mapping of static NAT. Explaining the difference between PAT for employee browsing and static NAT for servers demonstrates situational design judgment, the kind textbook definitions alone can't replicate. For critical networks, the business cannot afford a single point of failure. This introduces the requirement for high availability. This animation shows stateful failover in an active standby configuration. A primary firewall processes traffic, while a backup waits. The key is stateful. The active firewall continuously synchronizes live session data, like phone calls, directly to the standby device. Because the backup already has the live connection data, an active user call will survive the hardware transition with zero perceived downtime. The secondary unit seamlessly picks up the packets right where the primary left off. The business trade-off is financial. You're paying for a secondary hardware appliance that sits completely idle, processing zero traffic until a disaster actually happens. High availability moves the conversation from simple packet routing to true business continuity. It proves to an interviewer that you understand the financial stakes of a network outage. Let's contextualize what these technical concepts actually mean for your interview. Hiring managers ask about ASA firewalls to gauge if they can trust you with their production network, not to test your rote memorization skills. If you are applying for a junior role, you should lean heavily on the definition and example phases of the framework. You need to prove you know what the components are and how they behave. This chart shows efficient memory triggers. Remembering inside is 100, DMZ is 50, and outside is 0 are low-effort, high-impact facts. For mid-level or expert roles, your strategy changes. You must weigh answers heavily on the use case to demonstrate business value. By emphasizing use cases, like how the DMZ provides security segmentation or why clustering increases performance, you stop sounding like a technician and start sounding like a strategic architectural engineer. Be aware of the trade-off. When you claim architectural knowledge, the hiring manager will pivot. Expect much harder, deep-dive scenario questions to verify your depth of experience. Now it's your turn to practice. Use the DEU framework in the comments below to answer the question, how does failover work in an ASA? We'll review your answers just like a real interviewer would. Walking into a technical interview with just raw knowledge leaves you exposed to anxiety and rambling. Relying on a structured framework like DEU gives you the exact boundaries you need to answer clearly, confidently, and efficiently.